Maxime Ingremeau would think about improved at infinity bounds for eigenfunctions on randomly perturbed Schrödinger group.
Okay, thank you very much for the introduction, and thanks to the organizers for the invitation. It's a pleasure to be here. So today I'm going to talk about some joint works with Martin Vogel, who is in Strasbourg and who is here, and with Alba Garcia Ruiz, who is in Madrid and not here. And so what I'm going to present is about some L-infinity bounds of eigenfunctions of randomly perturbed Schrödinger operators. And before talking about random perturbations, let us start with genuine Schrödinger operators. And first of all, with the Laplacian. So in most of the talk, we'll be working on a compact manifold, and there you have an orthonormal basis made of eigenfunctions of the Laplacian. And so you can do the same thing with a bounded domain in RD with some nice boundary conditions, like Dirichlet boundary conditions, for instance. And the big question is, what do these eigenfunctions look like? So here is a picture which I took from some physicist's paper. So in the first case, you are in a disk, so there are lots of symmetries. The classical dynamics is what's called integrable, and the eigenfunctions look very simple. You can compute them explicitly, and they can concentrate in some part of the domain. And in the second picture, you are in a cardioid. There are fewer symmetries. The classical dynamics is chaotic, and the eigenfunctions look much more complicated, almost random, and completely equidistributed. And, well, you can play the same game on a manifold. So on a sphere, you have lots of symmetries, and so you know what the eigenfunctions are. They are the spherical harmonics, and you can build some spherical harmonics which are very simple, like this one, very, very symmetric. While on a manifold of negative curvature, things tend to look much more chaotic and complicated. And so in this talk, we'll be interested in the limit when lambda j goes to infinity. So rather on this part of the picture, and more in situations with few symmetries and more chaotic behavior, so more on this part of the picture, which we will try to understand. And since there are only civilized people here, we will switch to semi-classical notations. And so I will use the semi-classical parameter h. It's going to be 1 over square root of lambda, so it's going to go to 0. And the eigenfunction equation now writes minus h squared Laplacian psi h is equal to psi h. So that's the first kind of problem we're going to consider. And the second kind of problem we will look at is to look at semi-classical Schrödinger operators. So here we are working in RD with a potential which is a confining potential. So it's smooth, and it goes to infinity as x goes to infinity. So you can take v of x to be a norm of x squared, for instance. And so there you still have an orthonormal basis of your operator, which is now minus h squared Laplacian plus v. And here the eigenvalues and eigenfunctions do depend on the parameter h. So we'll be interested in the regime where h goes to 0, but the eigenvalues are in a fixed interval. So if you want, this situation is a bit similar to working with a domain in RD, but instead of imposing some Dirichlet boundary conditions, you have some kind of smoothened boundary conditions. And so what are we going to be interested in? Well, we'll be interested in L-infinity norms of eigenfunctions. And so why do we want to study those? Well, there are many motivations, but let me highlight two. So the first one is that L-infinity norms are very much related to the phenomenon of localization and delocalization of eigenfunctions. So when you have small L-infinity norms, it's a way of saying that eigenfunctions are delocalized. So usually, when you're working on a manifold of negative curvature, then the geodesic flow is chaotic, and what physicists expect is that eigenfunctions should be delocalized so that the eigenfunctions should have a very small L-infinity norm. So usually when people talk about delocalization of eigenfunctions, very often it's in the language of semi-classical measures which Clotilde introduced just before. And we'll have some other talks about this by Samir Diatlov and by Gabriel Rivière later this week. So so typically the kind of thing you want to look at are the eigenfunctions where you take their modulus square, you multiply by dx, so it gives you a sequence of probability measures, and you want to understand their weak limits. And a big question is the quantum unique ergodicity conjecture, saying that these measures should converge to the uniform measure. And so there have been some old results of quantum ergodicity, which Clotilde presented, and some more recent advances, which I think Samir Diatlov is going to talk about later. But the big thing in this semi-classical measures business is to understand if the eigenfunctions how much they can concentrate on one single geodesic. So on the sphere, we know that it is possible. We can find some families of eigenfunctions which do concentrate on just one geodesic, but well, we believe that this, and there are some results saying that this is not the case in negative curvature. And so my point is that, when you study semi-classical measures, often you want to say that eigenfunctions don't look like this spherical harmonic, while when you look at L-infinity norms, what you want to say is that eigenfunctions do not look like this spherical harmonic. So these are two very special spherical harmonics which are very localized in some sense, and you want to understand if eigenfunctions look like do not look like this or do not look like this. So these are two very complementary ways of studying delocalization of eigenfunctions. All right, so that's kind of one motivation. Another one is that L-infinity norms are very often related to the question of remainders in Weil's law. So to understanding how you can count the number of eigenvalues in some intervals, say. So indeed, well, there are many situations where you have a large remainder in Weil's law. For instance, if you have large spectral degeneracies, like on the sphere, and then you can build some eigenfunctions with large L-infinity norms. So there is no direct link between L-infinity norms and Weil's law, but very often what people do is to study the harder problem of local Weil's law, and it captures both features. So my point is that if you are interested in studying the remainder in Weil's law, well, often studying L-infinity norm is a good, easier problem to start working with. So that's another motivation. Now, enough motivations, and let us move to the existing results, existing upper bounds for L-infinity norms of eigenfunctions. So the first result is a rather old result of Kumovich, Romander, and Levitin in the 50s and 60s, and it says that on a compact manifold, the L-infinity norm of the eigenfunctions cannot grow faster than h the 1 minus d over 2. And so this is valid on any compact manifold, and this inequality is saturated by these functions which we saw earlier, so these spherical harmonics, which tend to be very large on the north pole and on the south pole, which you cannot see. So that's for the Laplace-Beltrami operator, and when you are working with a semi-classical Schrödinger operator, you have exactly the same bound, and it was proved a bit later by Koch, Tataru, and Zworsky. So now these are very general bounds, and the question is, can we improve them, and particularly in negative curvature, as I said before. So there's a conjecture about this, a conjecture by Peter Sarnak, which says that on a hyperbolic surface, so on a manifold, on a surface of constant negative curvature, the L-infinity norm of the eigenfunctions should grow less rapidly than any negative power of h. So this is just a conjecture. Now, what do we know? Well, not that much. The best result so far is a theorem by Bérard. It's a theorem which goes back to the 70s, and it says that in negative curvature, you can improve this very general bound by a factor 1 over square root of log h. Sorry. So this is somehow a very weak improvement, but it's very hard to do better than this for some good reasons.
What is lambda h and what are the assumptions on
So in this situation, lambda h is always going to be in a fixed interval, say between 1 and 2, and it's h which goes to 0, gives the oscillation.
what assumptions on
V, it's a smooth potential, and it is confining, so it grows at infinity, and probably you need to impose a polynomial growth at infinity somehow. Of course, if there are any other questions, feel free to answer. Okay, so it's very hard to do better than this, and well, the only
Maxime, there's a question. Is there a rationale for Sarnak's conjecture?
well, the whole philosophy of quantum chaos, saying that when the classical dynamics is chaotic, eigenfunctions should equidistribute. That's one motivation. There are some somehow stronger conjectures by physicists, like Berry's conjecture, Berry's random waves conjecture. In its strongest form, it would imply something like this. And well, of course, Sarnak is an expert in analytic number theory. So I guess that in some arithmetic case, you can relate this to some conjectures in number theory. So that's one thing. And last, and probably the most important, you can do some numerics, which would show something like this.
Is it Berry conjecture?
It depends. Okay, it depends on which interpretation of Berry's conjecture you take. It's not completely clear.
Okay, that's,
the strongest version of Berry's conjecture implies something which is wrong. So you have to choose correctly. And the weakest one implies something, does not imply this. So you choose. Okay, so the only case when we know how to improve this is in the arithmetic case for arithmetic eigenfunctions. So there are eigenfunctions of some other arithmetic operator, and there it's a result of Iwaniec and Sarnak, and they can improve over this bound by little power of h. They gain h the 1 over 24. So using arithmetic, they can do a little bit better than the general bound. And it's the only polynomial improvement in negative curvature, I think. Now, the whole question in this talk will be, sorry about that. That's a bit scary, so I should probably find a way of removing the sound. Okay, how can I do that? That's it. Shouldn't happen again. Okay, so the whole question is, can we obtain something better than this or this if you are in a generic or random setting somehow? Before doing this, I would like to discuss a bit more these bounds, to discuss some other related works. So first of all, I said that Berry's result, is the best thing we have so far, and it's a rather old paper, almost 50 years ago, but actually people have been working a lot in this direction recently. So this kind of estimate has been generalized to manifolds without conjugate points, and so that was a result of Bontonneau, and to much more general manifolds by Kanzani and Galkovsky, and there were earlier works by Zort, Teldich, Galkovsky. And also, this result is about L-infinity bounds, and many people worked on the other LP bounds, and it was a lot harder, and they could also gain some power of log h. So these were some more recent results of Hassel, Tacey, Hezario-Rivière, Blair, Zog, and so on. All right, and I would like to mention that there are also some lower bounds, which were given by Rudnik, Sarnak, and then Milicevic. And so these are in the arithmetic cases. In dimension 3, they can build some eigenfunctions whose L-infinity norm grows polynomially, like 1 over square root of h. And in dimension 2, they can build some eigenfunctions whose L-infinity norm grow more slowly than any power of 1 over h. It more rapidly than any power of log h. So this is coherent with this conjecture, but it tells you that you cannot really expect more than this. And also, it's really not clear what to conjecture about L-infinity norms in dimension higher than 3 or in variable curvature. Because as I said, one of the main motivations was numerical experiments, and numerical experiments were only done in dimension 2 for constant curvature, because it's the easiest situation to do numerics. And well, I hope to be able one day to do some numerics in a higher dimension, in variable curvature, to know exactly what we can conjecture. That's not for today. Today, as I said, we are discussing generic and random settings. So first, what do we mean by generic and random? Of course, there is the old debate of should generic be understood in a topological or probabilistic sense. That's one subject of discussion. But there are many ways in which you can introduce some genericity, perturbation, randomness in the problem. So let's follow the discussion of these two young people who present all the ideas people had so far. So first of all, well, when you are on a manifold with a large spectral degeneracy, like on the sphere or on the torus, instead of working on some fixed eigenfunctions, you can pick eigenfunctions at random in one eigenspace. And so people have been doing this, like for instance, Van der Kam and Burk-Lebeau on the sphere, and they can show indeed that with very large probability, your eigenfunctions will have L-infinity norm growing less rapidly than any power of the eigenvalue. And actually, they can do more than this. They can be more precise on the remainder here and have some log here. So that's very nice, but of course, you can only play this game when you are on these very special manifolds where you have large spectral degeneracies. So on more general manifolds, what you can do is, instead of taking eigenfunctions at one energy level, you can take them with eigenvalues in some spectral interval. And you can play the same game and obtain the same kind of results, but of course here you're not talking about eigenfunctions anymore, you're talking about linear combinations of eigenfunctions. There are more quasimodes, and it's not exactly the same kind of problem. So another direction would be to change your operator by adding a small random potential or random magnetic field, or change the metric in a random way. Or, I mean random or generic or whatever feels good. So I think the first results in this direction were by Kanzani, Svarathasan, Jacobson, and Toth a bit more than 10 years ago. And so what they did is they started from some eigenfunctions of the unperturbed Laplacian, and they added a metric or magnetic perturbation to their operator, and so they propagated their eigenfunction by these random evolution. And then, well, they take the modular square of this and average over the perturbation, and they can show that this is not too large. So what does this mean? This does not give any new bound on the L-infinity norm of any single operator. But what it tells you is that if you have an eigenfunction which is very concentrated at some point, like on the North Pole, for instance, and you start moving it in this noisy way, then yeah, if it was very large on the North Pole, maybe it can still have a very large L-infinity norm, but it should be large at another point. So somehow that's interesting, but it doesn't tell you that generically you have better L-infinity bounds.
So is that supremum over x?
For every x, you have something like this. So yeah, I guess you can take the supremum. I'm not pretending to be super precise when stating these results.
You're integrating over the u.
Yeah.
So the x is just...
for every x, you have something like this. Okay, so that's one idea. And another result a little bit in this philosophy, which I mentioned earlier, is by Kanzani and Galkovsky, and they can show that actually the logarithmic improvement proven by Bérard in negative curvature, well, you can have it for any metric which is somehow generic. You don't need to have negative curvature. And here, generic is not in the sense of probability or in the sense of topology. It's in a strange sense, which is called predominance. And well, one of my aims to come to this conference was to ask Jeff Galkovsky what does predominance means, but he couldn't make it. So, I mean, he couldn't come, not to explain to me what predominance is. But, so we'll have to wait until the next conference to know exactly what this means. But that's a very nice result. And last but not least, I would like to mention that another way of looking at generic manifold somehow is to work not with one single manifold, but rather to look at the limit of large manifolds, like large sequences with more and more complicated genus. And doing this, you can look at random covers or taking random metrics in the moduli space, for instance. And this is an approach which is quite different from what I'm going to present today, but which has been very popular lately. So there have been some logarithmic improvements on L-infinity norms by Gilmore, Lemasson, Salsten, and Thomas. And also there has been lots of works on other questions in these kind of limits of large manifolds by many people in the room. But, well, these are slightly different problems. Okay, so for today, we're going to stay with this kind of perturbation of adding some small random potential or something else to the operator. And so the result that I'm going to present is more in the spirit of this, if you want, or of this. And of course, the big question is, well, how are we going to do this, and what size should the perturbation have? You see in these results, somehow we change the metric or the operator by a perturbation of size which can be small, but which is like epsilon, independent of h. And you can wonder if you can do the same thing with smaller perturbations of size O of h, for instance. So of course, both are interesting. In these results, you can say, well, if you have in this result, for instance, you can say that for one perturbation of the metric, you fix the perturbation and you have bounds on all the eigenfunctions. While if the perturbation depends on h, it can be a bit harder to explain to people what it means. But on the other hand, you can say that the smaller the perturbation is, the more information it gives you on the initial problems. So it's interesting as well. But yeah, in the talk, as you will see, we are going to consider perturbations of an intermediate size O of h to the alpha, for alpha between 0 and 1. All right, so that's the end of my introduction. And now let me move to the theorem. So here I've just recalled the existing bounds. And now let's move to the theorem we obtained with Martin Vogel. So here I'm being a little bit imprecise. I will explain everything in a minute. So the result says that you can perturb your semi-classical Laplacian. Oh, sorry, with Martin we are on a manifold of negative curvature. And so what I say is that we can perturb the operator by some small pseudo-differential perturbation, which is somehow generic, and such that for this new operator, the eigenfunctions satisfy some better bounds. Instead of the 1 minus d over h to the 1 minus d over 2, you gain h to the gamma. So here we have for some explicit positive gamma.
Are you going to explain which kinds of differential perturbations?
Yes, don't worry. I'm going to explain everything. But so we have some models of perturbations for which we can have a polynomial improvement on an infinity norms. And so, in this paper with Martin, we were working in negative curvature because, well, we had been working on some perturbations of Laplacians in negative curvature for a long time, so we were only thinking about this. And then we realized that negative curvature is not really necessary. So yeah, that's something we are doing with Alba Garcia Ruiz. It's a paper which should be finished very soon. And so here we consider, we are working in RD with confining potentials, so semi-classical Schrödinger operators instead. And what we can show is that the same result, if you perturb it, should be a pH here and not a, if we perturb it in a generic way, then we'll have the same kind of polynomial improvements. And so, yeah, the gamma we have here is, well, it's explicit, and if you choose well the perturbation, you can have 1/7 in dimension 2 and 2/9 in dimension 3. So, well, it's far from being 1/2 or d minus 1/2, but it's not 1/1,000,000,000. And so now, of course, the dream would be to be able to take, for these perturbations, a small perturbation of the metric, or a small potential, or a typical metric in the moduli space, or a magnetic potential, whatever you want. That would be one part of the dream. And the other part of the dream would be to be able to go to gamma, which would be d minus 1/2. So it would be a way of saying that Sarnak's conjecture holds in a generic way. That's not what we have. As I said, the gammas are not that good, and the models of random perturbations are not that natural. So I'm sorry, the next slide is going to be a little bit technical, and the kind of perturbations we have are not the nicest one you can think of, but it's the only thing for which we can prove this polynomial improvement so far. So now let's move to the hard-code slide, where I explain what the perturbations are. So here I recall what the theorem is. Well, I merged two theorems into one. And so to build our random perturbation of the operator, we are first going to build an auxiliary family of operators. So here we are going to start with our semi-classical Laplacian or semi-classical Schrödinger operator, and we add some small pseudo-differential operator to it. So here, this perturbation, it depends on two parameters, alpha and beta. So alpha is going to be between 0 and 1, so it's going to be a small perturbation, and beta is going to be smaller than 1/2, so it's a nice symbol if you want, and they should satisfy some extra conditions. It's not empty. Okay, and so what exactly is this symbol? It is something which oscillates and decorrelates at scale h beta. So what you should think of is, well, instead of writing equations, let me make a picture. It's a bit like in the Anderson model, for those of you who know about it. You should think of your symbol Q to be a sum of bump functions like this. And so the bumps are all of size h to the beta. They are all of height h to the alpha, and each of them, you multiply them by some random variables which are bounded and IID. Okay, and so if you want, it's a little bit like the random potentials you have in Anderson model, except that you have these fancy powers of h here. And also, we are not covering just the manifold, we are covering the cotangent bundle, or R to the 2D, if you want. So actually, you don't need to cover all of it, just the critical energy layer, but well, that's just a detail. Okay, so that's an auxiliary random operator, and it's not the one which appears in the theorem. The one which appears in the theorem is this guy. So we take our semi-classical Schrödinger operator and we conjugate it by this random evolution. And so I'm going to say a bit more about this later. And the statement of the result is to say that with probability, so if you build these random operators like this, then with probability 1 minus O of H infinity, so very large probability, all the eigenfunctions of this operator with eigenvalue in some fixed interval, for instance, 1/2, 2, satisfy the improved L infinity bound. And so I would like to mention that these operators, you can understand them a bit better by using Agarov's theorem, which Clotilde told us about in the previous talk. By Agarov's theorem, these operators are actually of the form our Schrödinger operator plus some small pseudo-differential perturbation. But the symbol which you have here is something a bit complicated. It oscillates, it's in a nice symbol class, but how its correlations are a bit complicated. And a remark is that the eigenfunctions of these new operators, they are just the initial eigenfunctions of your Schrödinger operator, which you propagate by this noisy perturbation. Oh, sorry, there should be a over H here. And yeah, so if you don't like the result, if you don't like this operator, another way of saying things is that the result is about taking one eigenfunction and propagating it in a random, in a noisy way, and saying that with large probability, its L infinity norm is better. So somehow it is a bit similar to the results of Jacobson, Esvaraf-Hassan, Kanzani, and Toff, which I presented before, but we don't need to average over the perturbation. And yeah, I want to mention that T is going to be fixed. You can take T equal to 1 if you want your favorite choice of units. And yeah, we're not going to let T go to infinity. Okay, so now I wanted to say a bit about the proof. Are there any questions about the result? Yes.
Just to understand how different it is, I guess it's a Baker house of type argument, but if you're just adding this between the HW to your initial operator rather than conjugating with it, with the evolution of it.
Okay, well, your question is, what if we work with this instead of this? And we try to understand the eigenfunctions of this directly? That's a very good question. We don't know how to do it so far. I mean, we are starting to have ideas, but this would be harder.
But is it that much of a difference if in terms of what you actually get? But the problem is just
yeah. Somehow you have a small perturbation of the operator, so the associated classical dynamics is the same, for instance, but the operators are quite different. For instance, because of this, this operator has the same eigenvalues as the initial operator.
Yeah,
so cannot hope to improve Weil's law or anything. While for this one, you can expect that generically you will have something better, for instance.
The reason I'm asking, if you take Laplacian plus potential and then you get your operator and take e to the it times your operator, it's not the same as e to the it potential times e to the it Laplacian, because they don't commute. But for small t's, it is the same. For very small t's, it's almost the same. So it's your theorem for sure tells something about the original one. So effectively,
No, here t.
dividing by h bar. Yeah.
We are here. T is fixed, and of course, if you let t go to 0, the theorem is not going to work anymore. Okay, we could take t to be some small power of h and still obtain a similar result, but you cannot hope to let it go to 0.
Can you say that there is some window of t depending on h for which your result actually say something about the original operator, about the additive perturbation?
Well, the result is going to hold for t's for which you cannot say anything about the initial operator. Of course, you cannot have something for free. You cannot, because, yeah, if you remember our result, of course, in negative curvature here, you expect that you don't really need the perturbation to have some very nice bounds. You expect that adding some randomness is just here to help you, like it's the cherry on the cake. But of course, in this result, we ask nothing about the classical dynamics or anything. The n-infinity norms of the eigenfunctions of the initial operator could be very large, and here the randomness really helps us. Okay, thanks for the question. Yes, Selim.
I'm just asking for some decision on this question. So what you're saying, because at the end you have this formula that's p omega h. It's very much of the form as p tilde, right? It's ph.
Yeah, it's a similar form, except that here the symbol is more complicated.
So is it that in the original operator you know the law of the perturbation?
Here, yes.
And here you don't know the law of q.
Yeah, you can do, you can apply Egorow's theorem, and so this, well, it would be this transported by the classical dynamics minus this not transported, something like this. So it could be a bit more complicated, but you can describe it. It's not very interesting, but here. It is, okay. Well, you choose what's interesting.
You have to avoid some bad times. So for instance, if you have a sphere, you take pi for the times.
Yes. Yeah, that's not a problem. Well, strictly speaking, the results are only negative curvature or for confining potential, but the one with alba, it could adapt on a manifold, and yes.
Confining potential could be a harmonic oscillator.
It could be, and you don't need to avoid...
periodic flow.
Exactly, yes. And you don't need to avoid special times. Any other questions? Yes.
To give just a gist of what the eigenfunctions look like, you start with a very large eigenfunction, like zonal spherical harmonic, or for the harmonic oscillator, like a Gaussian modes. Like, does it spread a little bit the eigenfunction, or is there any intuition in that?
I think it's better if I present the ideas of proof, and then we see if we can have any intuition from this. I'm not sure, but I don't think we can explain very well how what the eigenfunctions look like. We should try, yes. But, okay, so let me give ideas of proof of this result. Well, first, how do you prove any result in quantum chaos? As far as I know, there are only two strategies. So since we have most of the experts in the audience, they can tell me if I'm wrong. So if you want to see things in a very, very naive, rough way, I know two strategies. First approach is that in some situations you have an explicit expression for the eigenfunctions, or there are eigenfunctions of some other operator. So these are in some arithmetic cases. It works on the torus or on arithmetic hyperbolic manifolds. And these were done by, this approach was followed by Bourgain, Lindenstrauss, Sarnak, Rodnik, many others. And the second idea, which is more that of Berard and Taraman, and then Masher, Dyatlov, Jean, and so on, is more to study the propagator of the of some wave equation. So the general idea is that you start with a nice basis of functions in which you can express your eigenfunctions. So, for instance, Dirac masses, WKB states, or Gaussian coherent states. We're going to see those later. And then you want to propagate them by the wave equation or Schrödinger equation 2 times as large as possible. Okay, and these two steps are quite well known. And then you have to be smart and deduce something about the eigenfunctions from the information about the propagator. And it is in this third step that people have to be really smart and use some entropy or some fractal uncertainty principle or that's where people used to have new ideas. And because in the second step, we are quite limited. We cannot go to times larger than a constant times log h. And that's the reason why in Bérard's paper, Bérard's results, we cannot have improvements that are better than logarithmic. Okay, so this is a very schematical picture. Now, let's see how our random perturbations enter into this general strategy. Well, the nice thing here is that we know that the eigenfunctions, we know already what they are like. The eigenfunctions of our random operators, they are just initial eigenfunctions which we propagate in a noisy way. So first, we don't need to be smart and do something about step 3. We can directly relate the properties of the eigenfunctions to properties of the propagator. And secondly, we are only working at finite times because we fixed t. And so in step 2, we don't need to go to large times. So all we have left to do are the easy steps somehow. And well, let me explain how we are going to do this. So first of all, we need to take a nice basis of functions. And so let me start with the proof of the result with Martin in negative curvature. So the basis of functions we want to work with are Lagrangian states. So functions of the form a of x exponential I over h times some phase whose gradient should have constant norms. So these functions are somehow the analog of plane waves on manifolds. They look a bit like this. Every point you have one direction of oscillation. And a more formal way of saying this is that these functions are micro-localized on some Lagrangians and manifolds. All right. And so the fact we're going to need is that eigenfunctions of the Laplacian can be decomposed using such functions. They can be decomposed as a sum of plane waves, if you want. And so the plane waves are going to be normalized. You have a kind of Parseval inequality. The manifolds which we have are well separated from each other at a distance of the order of h. And the important thing is that the number of elements in the sum is like h to the 1 minus d. So if you wanted to decompose like a general function, you would need more h to the minus d. And the fact that we are working with eigenfunctions gives us this extra power of h. So how do you prove this? It's quite standard. You use some Fourier integral operator to have some quantum normal form. So you reduce to a very simple situation. You reduce your operator to something very simple, and then you just use a Fourier series. But, well, this is already very nice, because from this decomposition and the Cauchy-Schwarz inequality, you can recover the bound of Hermander, the h to the 1 minus d over 2 bound. So of course, it's not really a proof, because I've lost some epsilons a little bit everywhere, so it doesn't give you the exact power. But what's really nice about this is that we all know the Cauchy-Schwarz inequality, and we know when it is an equality. We know that in Cauchy-Schwarz, if you want this to be large, it means that you have a lot of terms which are not too small, and they should have similar faces. And that's what we're going to try to play with. We're going to use our randomness to avoid having similar faces. And we will want to have some destructive interferences, if you want. And to do this, I need to explain about the propagation of Lagrangian states. Because, you remember, step 1, fix a family, a basis of functions, and step 2, propagate them. So how do you propagate Lagrangian states? That is something which is quite standard for unperturbed operator. It's called the WKB method. And it tells you that if you propagate a function like this, like the red one by the Schrödinger, semi-classical Schrödinger equation, during a small time, what you get is still a Lagrangian state. So has the same shape, and it's micro-localized on a manifold which is just the evolution of the initial one by the geodesic flow. And the amplitude just satisfies some transport equations. This is super standard. What is less standard and not very surprising, but hard to write down properly, is what happens when you have your when you add your random perturbation, when you have your noisy evolution. And well, there what you get to the first order, you have exactly the same amplitude and the same manifold here. And the only thing you gain is this extra random phase. And what is this phase? Well, if you are looking at your evolved Lagrangian state at some point, say here, so it means that classically you went from here to here, and what you need to do is to integrate over this trajectory the symbol of your random perturbation. Okay, so you have an explicit expression, quite simple, for the phase. All right, so now let's move to the end of the proof. Now we need to regroup our Lagrangian states. So remember that we decomposed our eigenfunctions as a sum of h to the 1 minus d Lagrangian states, and when we propagate them, what we get is, well, a sum of these propagated Lagrangian states with some random phases. And now we are going to fix the time t, fix the point x, and so we can just look at this phase as being a sum of things, numbers, times some random amplitudes. And now we can start doing a probability, or try to. And the first remark is that if these random phases were independent from each other and uniform between 0 and 2 pi, then it would be very easy to conclude and have much better, we will have much better bounds. So this is something you all know, but let me recall it. It's just the fact that if you have a sum for L from 1 to n of, say, some numbers like this, and you try to bound it, well, in general, the only thing you can say is that it is smaller than n. But if these are random phases, so if the theta n are random and independent, and if they are like centered, so if the expectation of exponential I theta n is 0, then you have all sorts of inequalities which look like the central limit theorem, which tell you that this is going to be smaller than n to the 1/2 plus epsilon. You should probably add a constant. And so this would be with large probability. Okay, so I'm sure you have already seen things like this. And well, so what I'm saying is that if here we had phases which were independent and with this centering condition, we could have bounds like h minus epsilon. Now, the bad news is that it's not what we have. The phases are not independent, so we cannot have bounds as good as we would like to. And so the idea then is going to be to regroup, well, to divide this sum into packets. So here we are going to rewrite the sum as a double sum. We'll have a sum over packets such that if you have two elements of the same packets, they correspond to Lagrangian manifolds which are far from each other. So if you want, if your Lagrangian manifolds were represented by points like this, you would like to make one packet with all the red points, one with all the blue points, but I realize that the colors are so bad on this screen that it's probably not a good picture. But anyway, so the nice thing is that in each packet, the faces you have are independent. So why is that true? Imagine you take two elements of the packet, so you have two Lagrangian manifolds, like a blue one and a red one, and they are far from each other, and you look at their contribution at some point x. So what you need to do is, well, you have one classical trajectory, one geodesic going from the red manifold to x, another one from the blue manifold to x, and the thing is that they are always far from each other at a distance much larger than h beta. They are far from each other in phase space, and so when we integrate our random potentials over these trajectories, the two trajectories will only see different potentials. They will see different random variables, and so they will be independent from each other. So that's the idea. And also, we can say that the expectation of this exponential to the exponential I times the faces is something small. To do this, you need to do some non-stationary phase in large dimensions. So this is just integration by parts, but quite hard. It took us a long time to do this, but I'm not here to teach you about integration by parts. I'm not going to mention this. And now, well, what you can do is that in each packet, you have all the tools to play this game. And so in each packet, you can play exactly this game and say that with very large probability, the modulus of the sum squared is smaller than the sum of the modulus squared. And then, so it means that with large probability, you have some interferences between the terms, giving you a small infinity bound in each packet. And then when you sum things, well, you have gained something at the end. And so you gain a power of h. And well, I'm not going to count power of h here, but you gain something. Okay, so to conclude, I would just like to mention a little bit what we're doing with ALBA, and so the proof for the confining potential. So here, it's not a good idea to use Lagrangian states because they can develop some caustics and so have large L-infinity bounds, L-infinity norms. So rather, we are using Gaussian states. So they are functions which are well, quite localized around the point x0, and in Fourier space, they are localized around some direction psi0. And then we can decompose any eigenfunction using sums of Gaussian states. So if you want, you can take a grid like this of Gaussian states in phase space x0, psi0, a grid of size constant times square root of h, and you only keep those which are close to the critical energy layer. That should be a 1, not a 0. All right, and here, so the number which you need is h to the 1/2 minus d, and you have the same kind of Parseval quality. But this time it's not elementary Fourier series. It requires the results of Dobschi's Grossman-Meyer, which are not completely trivial, far from trivial. Yes?
There's a question about the end of your proof.
Yes?
You didn't comment too much on the time that you are using.
Yes?
And so you say, well, because I have the impression if you take too large a time, things are going to be too dependent. If you take too small a time, you don't interfere enough.
I said time is going to be bounded. It's independent of h.
Like what?
Yeah. And that's enough to create these random faces. Okay, so you can propagate Gaussian states. So when you do it in a non-perturbed way, well, you have some expression. It still looks like a Gaussian state. And when you look at perturbed propagation, the noisy propagation, you have, well, as before, you have some random phase. And I would just like to mention the difference with what we had before. Well, the difference is that the number of terms we have is larger. It's not h to the 1 minus d, it's 1/2 minus d, because we need to take larger layers like this. And we have a prefactor, which is some power of h. So, well, these seem to be bad, but they are balanced by the fact that if you are studying a function around one point x, so something here, you only want to consider the Gaussian states which are close to x, and not all of them. So it gives you another power of h to play with. But now the bad thing is, if you want to do things this way, you need to consider the perturbed classical dynamics and not just the unperturbed one. Because, for instance, one Gaussian state, when you evolve it during time t, it could come here for some value of the random parameter and elsewhere for some other value. So we need to keep track of this, and it's a bit more involved than in negative curvature. But at the end of the day, we can do the same kind of proof, regroup things into packets as before, with things that are far away from each other and ugly colors. And, well, the only thing is that when we play this game, we need to be a bit smart to keep track of the fact that we are working only with Gaussian states which are centered close to a given point x. So we need to have an extra factor, including the probability that xk is close to x. And well, it took us a long time to understand that was the thing to do, but once we have done it, we can conclude the proof in a very similar way. And I'm almost out of time, so I would like to stop here. And thank you for your attention.
Any questions or comments?
Yes. Yeah, so once you have this decomposition into fairly understandable Gaussian states, do you expect that if you take, lower even LP spaces, like P is 4 or 6, you can explicitly write the L4 norm of the eigenfunctions with correlation of Gaussian states? And would you expect that if you put all your machinery in that, you could maybe improve, I don't know, L4 or L6 compared to SOG with your model?
So that's a good question. We have not thought that much about it. Well, what is sure is that you can do some interpolation, and for large values of p, you will get something better. We have not thought about smaller values of p. That's probably something which should be done. Thanks for the question. Yes, Zed?
Instead of using this confining potential, can you just work on the torus? Then you can take the potential to be 0. Your eigenfunction of the unperturbed operators are like sines and cosines exponential. Then the only thing you need to do is to understand how they evolve under this random semigroup. Is that easier to do?
It's not going to make a big difference. So, in principle, the approach with alpha would work on a compact manifold. We chose to do it with a confining potential, but it should be doable on any manifold.
No, but on the flat torus.
But on the torus, well, the thing is that on the torus, the eigenfunctions already have a rather small L infinity norm compared to the sphere. Yeah, not in higher dimensions, but in higher dimensions, what we gain is not that great. So
I'm asking
it could be.
You can gain something better.
I don't know. Yeah, maybe we can do something worse than the unperturbed case, but I'm not. I don't know if we can do better.
Test, I think, of the method. Because you keep saying that you emphasize that there are these two approaches. One is to use explicit things, and the other is what you're doing.
It was a very rough picture, of course, but.
I regret.
Okay, so we can try approach 1.5.
Maybe it'll be worse.
Which
is also interesting.
Yeah. No, it's a good question. Thanks. Thanks for asking it. Yes, Marshall.
Just curious, but so basically the problem is you have this constants depending on its CH such that an infinity norm is super than CH of an norm, and you want to find the optimal CH, or I think an upper bound at least for this. So I want to ask the complementary case. Do you know in your case if you have some lower bound, some interesting lower bound for this?
No. No, we don't have a lower bound. It would be super interesting, but the problem here, if you want, it's here. We are, we are dividing into packets, and in each packet we can understand quite well what happens. We could have lower bounds as well, but then of course when we sum them, we cannot say anything. You know, the sum of two small numbers is a small number, but the sum of two large numbers is not necessarily large. That's the whole problem. But it's a very good question.
Thank you. But yeah, maybe this. I had another question, but maybe you know it is interesting. But I mean, what I mean is, so do you know at least what is the class of this pH that gives you the optimal? So instead of considering basically a lot of possible pHs, just consider one class of pHs, which is going to 0, and none.
Sorry, I didn't.
No, sorry. So probably yeah. The fact is this. So you have you're putting a result for all pHs. So we're saying, what about considering just a sequence of these pHs? And so, do you know something about the sequence making this constant optimal, and what would the constant optimal in the case?
Would we have anything better if we were working with subsequences rather than I don't think this would help anyhow. The thing is, the same proof would work with linear combinations of eigenfunctions and give the same bound for linear combinations in small windows. So then it doesn't make any sense to extract. Well, I don't think it would be of any use to.
I was just wondering, for example, because in quantum integration there are some good results for sequences, but then there are somehow lectures for any sequence. I was wondering instead this case is smaller. Yeah.
No, it's a good question. I don't
Thanks
know.
so much.
Thank you.
At some point, you said that the BK need to be not small. I mean, that there are many of them which are not small. Or do you ensure this?
Where do we
show that they're not almost that the state is not a single.
No. I said that if you want to have a large L-infinity norm, you need the BKs to be of to have many of them which are of similar magnitude, and so okay, somehow it's here. If you want, we are using a Cauchy-Schwarz again here, and of course, if you can say that there is only one BK or a small number of them, like on the torus, for instance, then you can do better. Okay, thank you.
You mentioned in your introductory remarks that the random wave model gives rise to some incorrect predictions. What do you mean by that?
Well, okay, there are several ways of formulating Berry's conjecture, because you're saying that a sequence of deterministic objects behaves like a random object. So from a mathematical point of view, it's a bit unclear what it means. But if you believe in Berry's conjecture in the strongest possible sense, you would expect to have okay, yeah. So it's actually these results. This one a little bit, and even more this one. If you believe in Berry's conjecture in the strongest sense, you would expect here to have L-infinity norms which grow like some power of log h. And so this is contradicted by these results in dimension 2 and this result in a higher dimension. Now there are so
arithmetic for this arithmetic stuff.
yeah, for arithmetic surfaces, this would be contradicted. So of course there are several ways out of this problem because Berry's conjecture is true, as everyone knows. So maybe it's true only for generic manifolds somehow, or maybe it's true only around the generic points. And
isn't it? Are the arithmetic cases? Probably it's a question for them. The arithmetic cases are also the place where the BGS conjecture fails, right?
Yes.
So maybe it's just the definition of chaoticity.
No. They are chaotic. They are fully chaotic.
yeah, the negative
No,
curve.
Classically, they are fine.
They are
There are these pathologies.
chaotic dynamically, but spectrally, if you believe the quantum signature of chaos type of where you expect both very random wave conjecture and BGS conjecture to hold, then maybe this have to make symmetry.
The philosophy, to my mind, is that in classically chaotic case, the eigenfunctions and eigenvalues have to be random, unless it's obviously true, and obviously sometimes in retrospect. But once you find something that's wrong, and you find a good explanation which comes from arithmetic, then you just say it's pathologies and move on.
No, but I mean, the point here is that these are special families of eigenfunctions. So various random wave conjectures meant to hold for generic eigenfunctions, say full density subsystems. That's not the case here, right? I mean, we also say there could be sort of some localization of eigenfunctions, scars in some sense, and that is a different phenomenon, right? But they happen for very sparse subsequences. So I wouldn't say that this contradicts Berry's random wave hypothesis because it's more generic.
I only said that it contradicts Berry's conjecture in the strongest possible sense you can think of it. But of course, there are several ways out of this contradiction by working around generic points, looking only at generic surfaces or at generic eigenfunctions. There are many ways of, there are probably many many versions of the conjecture which are true.
Let's continue discussion on Berry conjecture.